Hello, good evening. Can you hear me? And can you see my screen?
Yes, sir.
Okay, let others join. We'll start up that. Let's wait for some time.
Okay.
Okay, let us start. Let others join in their own time. You can hear me, right?
Yes, sir.
Okay. So, this is the 10th week lecture. Mm, this is about gate drivers. We have one more weeks left of material, and since we synchronized ourselves by advancing one week, last week we do not have any such lecture. We'll maybe see if we can have a recap or some other discussions. So this week is about gate drivers. So broadly speaking, for silicon devices, there are two types of gate drivers. Okay, one is the sorry, one is say for BJTs or for thyristors, that is for the current control devices, and the other ones are for maybe MOSFETs or for IGBTs, that is for voltage control devices. Now, gate drivers, as you can understand, that they are required to turn on or turn off the devices. The devices require certain amount of charge or some other mechanism so that they can create the channel in them which can let the electric current flow through the semiconductors. Now, mm, thing is that gate drivers have certain requirements. First of all, power. It should be able to supply the required gate power, whatever the switch requires for operation. Secondly, which may not always be necessary, but it's better to always provide it, is isolation. And thirdly, what is required is protection of the devices. Now, in the lectures, mostly these two parts are covered. This is not covered. No, this is covered actually. There is an overcurrent protection, DSAT protection. This is there. So all of them are covered, I believe, in the for the requirements of gate drivers. Now, this session is going to be a very short session. Hmm, I do not think there is much to discuss unless you have many questions. So we can start asking questions now. If not from gate drivers, but from previous lectures also, if you have, you can ask. No question from gate drivers?
Sir,
Yeah.
uh, sir, in the last class, you have told in the one of the previous class that if we are driving a switch,
Hmm.
suppose we are driving gate with respect to source,
Hmm.
and the source is not grounded, and the
Hmm.
source is not yeah, and when the source is not at the ground potential, when it is like a floating potential, then there is a need for isolation.
No, it's not like that. Okay, go ahead.
Yeah, sir, I just want to know that anyway we need between source and gate, we need to give only uh, 15 volts or 20 volts, and then when we make it to zero, the switch is going to be off. So, but why the where the isolation need arises? Because anyway we are going to give only with respect to source, we are going to give 15 volts to the gate.
Okay.
Uh,
Suppose this is one leg of an inverter. Okay. Inverter circuit you all know, I think. So this is one leg of inverter. Say I'm drawing BJT or IGBT, whatever. Say I'm drawing IGBT. Sorry, like this. Now these two switches, if I call them S1 and S2, they require gate drivers. Okay, separate gate drivers. Now say this is the if not like this. So this is the gate driver of S1. Now this must be connected to the source. For IGBT it is emitter, for MOSFET it is source of the switch. For this one also it requires its own gate driver, like this. Okay. Now there is one common control circuit for this whole inverter. Okay, there is an electronic circuit which receives maybe a voltage of plus minus 15 volt. from some sources, so it has got some ground. Okay, this ground, the same. Okay, now what happens is, mm, inverter, you have six switches, so six outputs come from them. Now I am drawing only two outputs. Okay, now you see, if now this output also comes with a ground, the same ground as this one, right? Now what could have been done is, this could have been connected to an op amp, maybe, um, like this, I think. Negative feedback. The op amp. Now this thing well enough works as a gate driver, right? Now another gate driver here also the same way, and they directly go to the switch. Now the problem is, the whole control circuit has the same ground. Okay, so if the control circuit and the gate driver have the same ground, then these 2 points, if you look, this source or emitter and this source or emitter, they are now virtually shorted. Is it understandable now till now? All of them are connected to the same ground, same control circuit ground.
Okay. So, so all the gate terminals will be getting some PWM from the output of the control.
Yes, and the controller is the same. We are not having different controller for different switches,
Hmm.
right? We have one controller, and all the controllers are supplying the switch. The controller output
Okay.
goes to a buffer. Buffer means that has a capability of giving current to turn on the switches. Okay, and that
Okay.
is connected to the switch bases. Okay.
Hmm.
And we also have to connect the ground to the source of the switch or emitter of the switch, so that the gate current can flow, right?
Hmm.
Gate current must have a loop like this. Now if we do that, so this point and this point, they are virtually connected to the same ground, or in other words, they are
Yeah.
at the same potential, or they are shorted,
Okay.
right?
Hmm.
So what is happening now, these 2 points are shorted,
Okay.
right? Now we have a DC voltage source here for the inverter, right?
Hmm.
Now in this
Ah.
condition, if you keep it like this and then you turn, if you turn on S1, what is happening is a current is going to flow through S1, then this, like this. So the DC voltage is source is going to be short circuited.
Okay.
And where does, if you look at this blue path,
So S2 is supposed to be off at the time,
see,
but
S2 is supposed to be off, but it doesn't matter. S2 is anyway bypassed.
yeah, but it is conducting. Okay.
Is anyway bypassed. By normal inverter operation, we do not turn on S1, S2 together. Okay, but S2 is anyway bypassed to the control circuit ground.
Sir, bypass you mean it is flowing only through the switch, right?
Only to the switch, but you can understand, no, that this points, if I call this point A and if I call this point B, they are
Ah.
actually physically connected.
Yeah, yeah. Okay.
So the current,
Yes, I
short
understand.
circuit current, can flow through that physical connection.
Okay. Hmm. Okay.
So in such cases where the emitters or the sources of the switches are not connected, I mean in the power circuit, if they are not shorted together, then you have to give isolation to the circuit, to the gate drivers. Now
Mhm.
what do we mean by isolation? This thing is more or less same for all the this thing you can verify for a buck converter also, for not a buck converter, for a synchronous buck converter. If you see, mm, say you have a switch like this and you have a switch like this, right? So the gate driver 1, that gate driver 1, that must be connected like this, and the gate driver
Mm.
2 must be connected like this. And if I do not provide isolation, basically these 2 points are shorted,
Okay.
and they are physically shorted. It's not like a virtual ground or something. They're physically shorted through the
Mm.
controller.
Mm. Okay.
And when you turn on this switch, the current flows through this switch, then through this physical connection in this way.
Okay.
Let me draw it with some other color. Turns one, flows through, sorry, this switch, then through this, goes to the other. You will see that it is a very common practice to see when we draw buck converters, how we study or draw, we draw it in this fashion and all. Okay, but it is a very
Mm.
common practice to have the switch in this way.
Yeah.
Why so?
Because to take the ground as the reference, stiff reference to get.
No, even if I keep it there, it is a stiff reference. But the thing is, uh, say most of the time what happens is that the same smps from where we are supplying the gate, supplying the buck converter, we are also deriving the power for the gate driver. Okay, so
Mm.
this and this are anyway having the same ground. Now if you keep the switch here, you have to compulsorily provide an isolation to the gate driver, but if you keep it here, you can not use isolation. So if you make a
Mm.
buck converter like this, or
Mm.
maybe the flyback or forward converter primaries, if we do that we draw like this, in such cases, even if you derive the converter power supply and the gate driver power supply from the same DC source with the same ground, you need not provide an isolation.
Mm.
Isolation is not required in such cases.
Okay.
So this is why the switch is sometimes moved here. But people tend to provide isolation even if they have such a circuit, so that power spikes cannot travel back to the source, to the control side. Now, how this isolation is made? Okay, there are mostly two type of isolation. One is the opto isolation. Other one is the galvanic isolation. Now, not only that they are operate in different principle, but their means the signal that they transmit through the isolation are also different. We will look into it what it is. Say I talk about opto isolation first. Okay, now this is my controller circuit. Okay, now my controller circuit is giving me some signal. There are several ICs. I think 4M35 is one optical isolator, and there are other things also. Now there is one optical isolator here, or also we call optocoupler. Optocoupler IC looks like this. It has a photodiode that emits infrared, and it has a phototransistor that is sensitive to that infrared, and they are packed in the IC like this. So this is the IC that you get. Now what you have to do is you have to connect a resistance and like this. Okay, so this is the control ground, and inside the signal is getting transmitted through optical isolation in this fashion. So the ground that you have here and the ground that you have here, blue. mm, just a minute, let me make it red. What you have here and the ground that you have here, they are different. Clearly they have physical isolation, but the problem is this optical channel cannot provide you enough energy which can turn on, or enough power which can turn on the switch, right? So you have to have power also. Now most of the cases what happens, we have one source of all energy, all or one power source. Maybe it comes from a 230-volt supply, and then you use a transformer, or maybe you use an smps or whatever. Now that same smps supplies the control, right? So they have the same ground. Now this smps also supplies, say, another. Okay, now the thing is, this smps, okay, we'll go look into it. Now the thing is, this thing cannot drive the switch, so we need to have a driver circuit. Okay, this can be driver IC. For example, I used to use this one sometime back. 13315. These are MOSFET driver IC, MOSFET HB driver IC. But this requires some power, right? This requires some power, and I cannot connect this to here, because if I connect it here, I have to connect the ground also, and if I do that, my isolation is lost. Whatever isolation I got through the smps, got through the optocoupler, that is lost. So what I have to do is, I have to have another isolated power supply, and this must be isolated. Okay, this must be isolated power supply. This may be a flyback, this may be a forward, but must be isolated. Once you do that, now this thing has this ground, and you can supply power using this, right? So if you have optocoupler, now this thing directly goes to the switch. This thing directly goes to the switch. Let me not draw a BJT here, because this IC is not for BJT. This thing then goes to the switch, right? So if you are going to use optocoupler, you also must have an isolated DC-DC converter somewhere, or a power source whose ground is not same as the controller ground, otherwise whatever isolation you got, you will lose that. Such kind of converters, gate drivers, are very much used for voltage driven devices, MOSFETs, IGBTs. And another
Sir,
type of, yeah.
so basically, wherever we need a difference in references, suppose some part of the circuit will have a potential at every node with respect to some other reference, and the other part of the circuit will be having a node voltages with respect to some other reference. So the references are different. We need isolation.
Yes, but our objective is not to have different references. Our objective is to avoid these kind of things.
Yeah. Okay. So same reference can sometimes uh, create short circuit like this.
Yes. So you cannot keep a physical connection like this. If you do not provide isolation, they will remain connected through the control circuit.
Yeah. Okay.
If you turn this on, not only this switch will blow, your control circuit will also blow. And your control circuit might be containing expensive things like microcontrollers and all, DSPs, or even
Basically,
FPGAs.
okay.
Yeah,
Sir, in power electronics, controller is mainly used to control the duty cycle, right?
the switches,
Or
when to turn it on, when to turn it off,
yeah, duty cycle of the switches.
frequency also.
Ah, okay. So, so that is the only purpose of controller in power electronics.
Hmm.
Okay. And one more thing, we are saying the galvanic isolation.
Yeah.
Sir, why there is a special term given to this? It can be said as a transformer isolation also.
Yes, yes. Same thing.
Oh, there is no specific reason.
No,
Okay.
same thing. Now, for galvanic isolation, the advantage compared to this optical isolation is that you do not need a separate power supply for it. You might have studied this galvanic isolation. This is nothing but a forward converter. I have a switch which is grounded, and the gate pulse comes here, and this is nothing but a forward converter, and it goes to the switch, which is mostly used to drive current, sorry, current control devices. This is a very popular circuit to drive thyristerized, I mean, drive thyristors in this fashion. So as you can see, if you have VCC or whatever voltage, this maybe is coming from an SMPS, okay, and that has the capability of supplying the gate power, and the transformer has also the capability of supplying the gate power. So you just turn it on, that would excite the transformer and supply the gate power directly to the secondary, and it will turn on the switch. So you do not need a um, separate power supply. The power and signal both are traveling together. The power is traveling in a pulsed fashion, and uh, what is that called, forward converter, here also you will require a reset circuitry. But since this is kind of low power, not means as high as forward converter, you can have a resistive reset also. Yes. Such pulse transformers are generally 1:1, and they are available readily in the market. In I have seen in plastic enclosures like this, cylindrical enclosures like this, maybe a handful large, with four leads coming out of them. You can directly install it in a circuit and use. Okay.
Sir, can you please repeat how the power and you said a statement that power and the pulse flows in the same manner. How?
Okay. So you know the operation of forward converter, right?
Yes, sir.
So this is nothing but a forward converter. Now
Okay.
I want, say I
Here
give a
we are
get pulse
using.
like this.
Ah,
I give a get pulse like this. Now when this get
okay.
pulse is high, then this switch is closed. This is coming from my control circuit.
Ah,
Okay. When
okay.
this is high, then this switch is closed. So what do we have? We have VCC across the
Yeah.
primary. So the
Yes.
same VCC appears here, and it drives the, through this path it drives the gate
Hmm.
of the
Yeah.
device.
Now the gate turns on.
Yes. Actually, one more thing that is important here is that for thyristors, we generally do not give a continuous gate current, unlike BJTs or MOSFET. That is because say if I have my, say, holding current somewhere here and latching current somewhere here, when you turn on the thyristor, once it goes below the latching current, even if you remove the pulse, even if you remove the gate pulse, that will remain turned on. The thyristor will remain turned on. So only a calculated small pulse is enough to turn on the thyristor. Okay, there is no need of giving a continuous pulse like this. That will create unnecessary loss in the device. You have to keep supplying this power. That is not required. But the thing is that it might so happen that due to variation of load or due to circuit properties or something, this current shows a nature like this, maybe, and you want this current to keep going like this. Now if you do not give a train of pulses like this, then once the current crosses this point, the thyristor turns off. And even if the voltage is more, even if there is enough voltage to forward bias the thyristor, it will not turn on here. So if you want the current to be like this, to keep it continuous, and you do not know the load nature, maybe how what kind of current is going to demand, then you give like this. Now you see, such kind of pulse is even more helpful. I shouldn't say helpful, is even more suitable for galvanic isolation, or galvanic isolation is even more suitable for cases where you have such kind of pulses. Because see, you have a transformer. Please, you can mute yourself. I will explain. uh, Galvanic isolation, if you see here, it is a transformer. So the transformer comes with a magnetizing inductance, right? Now these discussions we have already made two times at least, that there are two components of the current. One is the current component, that is the reflected load current. That is fine, no issue with that. But the other one is the magnetizing current. If you keep the if you keep this switch S on, then the magnetizing current will keep increasing. So if you want to give a continuous pulse like this, you have to have a large transformer that can handle this much of magnetizing current, or in other words, this much of flux. But if you, instead of giving this continuous pulse, if you give this train of pulse, what will happen? When you turn it on, the magnetizing current increases, the energy is stored. And when you turn off the switch, the stored energy is dissipated in the resistance, this resistance R. Again, maybe it stops for some time, again turns on like this. So you can have a small transformer. So this is even more suitable, this galvanic isolation, where you have this kind of train of pulses. That triggers a small transformer.
Sir, you are saying here in this latching holding current discussion,
Hmm.
uh, even when the anode cathode current goes below the holding current, even at that time, if
Hmm.
you provide the gate terminal, if you provide the gate signal, then the thyristor will remain turn on.
Hmm. Hmm.
Oh, even when the holding current is less than.
No, just a minute. Yes, you see, it is say if this is the holding current, and by the nature of the load or whatever, the current was coming like this. If there is no pulse, it will anyway allow the current to drop, but
Yeah.
it will
Yes,
not,
sir.
it will not to go up once again. If there is no get pulse, it will not, it cannot go up once again.
Okay. Sir, anyway, for MOSFETs, we know we don't need this continuous current, right?
No, because MOSFET is not a, sorry, MOSFET is not a current control device. For
Yeah. So
MOSFETs, what do you have? Say we defined the capacitors, discussed this capacitor sometime back. You may remember.
yeah, gate to
There
source.
are three capacitors.
Mm.
In the data sets, in the data sheet, their exact names are not given. Rather, some summation is given. So
Yeah,
this
input
is
out.
the gate to source. This is the gate to drain. This is the drain to source. Okay, right. Summation of these two is given as CISS. These two is given as COSS, and from those values, if you know the equations, you can find out the individual values of these capacitors. Now, our when we are turning on a MOSFET, what we are doing basically is we are charging this capacitor.
Mm. Yeah.
So we have, say, a voltage source which switches between uh, gate voltage and zero voltage. Now when, sorry, now when this VG is high, what happens is it charges this capacitor, right? Now you have to keep it high, because if you make it zero, then this will start discharging and the switch will gradually go towards off state. So it's the current is exactly like a capacitor. If you give a step voltage to a capacitor, the current looks like this. So the current looks like this. The same kind of gate current you will get to see. Did I draw it right? Yes, you will get to see for a MOSFET. Now if you remove this
But
VG, what will happen is it will start discharging, so it will go towards off state.
yes, sir. But it will not take this much amount time, right? It will decay to zero much faster.
What?
This current is
This red current?
as you yes, sir. As you have drawn, it is decaying for the entire on time.
How do you know
Uh,
it is taking for the entire on time? Did I show on time anywhere?
but yeah, we have drawn this negative pulse here.
Oh, okay. You are comparing this and this. Okay, if you compare these two, then obviously no, this is not this long.
Okay.
Let me see if I have some waveforms to show you. Yeah. So these are some waveforms that we use here to teach postgraduate students. Uh, this is turn off. No, let us not talk about turn off. The same thing, turn on, turn off. Only the mirror image. Okay. So this is the turn on process of a MOSFET. I will copy this to our. Yeah. So okay. So you can see there are three waveforms here, right? One is the VGS, the gate to source voltage, the VDS, drain to source voltage, and the source current or switch current, drain current, source current. Now you see, this is the, it was off till now. It was off till now, say here, and this is the point where This is the point where we are giving the gate pulse. Okay, now this is a capacitor. This is nothing but an RC circuit. The gate circuit nothing but RC circuit. Now what happens to the voltage of a capacitor when you give a step? It increases like this and takes some time to of to reach maybe its whatever steady state value. Now there is some voltage. Say if I am drawing with VGS, there is some voltage which is called threshold voltage. Until the capacitor voltage reaches the threshold voltage, the switch is not turning on. Okay, until it reaches the threshold voltage, the switch does not turn on at all. Okay, the switch does not respond at all. Once this voltage reaches the threshold voltage, then only the turning on process starts. Now how does it start? Let me copy this once again. Now what happens, there is some voltage source here somewhere which can get current is flow through the drain of the switch. Now it flows through the drain of the switch. Now what happens is just a minute. Yeah, so the current first increases. The current in during this time, which is called the rise time, if you see in this time, the current increases and reaches to its peak value. So you see what is happening. If you look at VDS and IS, the current starts from here and reaches its peak value while there is no change in VDS at all. Well, there is no change VDS. If you see here, VDS is nothing but the voltage in the capacitor CDS. Okay, so during this time, CDS does not have the path to discharge. CDS does not have the path to discharge. So the switch is now conducting full current at this instant, but it is also have the full voltage across it. So this is why the switching loss comes. I have full current now, but the voltage is still full. Now beyond this, what happens during this time? During this time, the if I draw it in from here, CDS, this capacitor, most probably discharges through the switch. It discharges like this, in this fashion. Okay, so along this time, the CDS, this capacitor, drain to source capacitor, it discharges, and CDS is discharging means the voltage across the switch that is dropping to zero. And during this time, the capacitor voltage, the gate to source capacitor voltage is held more or less constant. So if you look at the gate to source voltage waveform during the switching, you will see for this time that voltage is held more or less constant. This is called the Miller plateau region, and the voltage is called Miller plateau voltage, this region. Sorry. And the voltage is called plateau voltage. After this, around this time, the switching is complete. Now whatever gate voltage you gave, the CGS will reach that much of voltage depending on the RC network timing, and it will hold there. So the switching actually takes this much time. The whole procedure is switching. And if you talk about, so this much is the delay time, this much is the rise time of the current, this much is the fall time. By this time the switching is complete in these three steps. And for this time, you have a switching power loss. So the power loss is something like this. If I draw the power loss here, is something like this. And the switch off process is just the mirror image of this thing. The same things occur. Yep.
Yeah, okay, sir.
Okay, anything else?
Sir,
Yep.
these silicon gate drivers, silicon dividers gate drivers we are studying now.
Hmm.
Uh, and nowadays, in our college, they say nowadays these advanced devices have came,
Hmm.
which are having very less time to
Hmm.
turn, which takes very less time to turn on and off. Uh, do these gate drivers still remain relevant for those devices as well?
I don't think, because extensive works are going on in those areas. People are doing PhDs on GAN and SICK device gate drivers, and they have other features, other things also. And those devices are also not very similar to these devices. They have their characteristics are different.
Oh. Even the IV characteristics itself
Yes, like they can
is
operate in some other quadrants also. Some things are there. I'm not very sure. I do not want to comment on them because I have not studied those things.
okay. Mm. But it will it they still be called as IGBTs and MOSFETs, or
Yes,
else it will
yes,
have some other name?
yes, MOSFETs.
Okay.
Okay. Okay, then we'll go into problems. We do not have many more things to discuss today, it seems like. If you want to ask something in between, you can ask. So, this is the thing that we were discussing some time back. It's a 1:1 pulse transformer, which is used to trigger the SCR in the adjacent figure. The SCR is rated at this much voltage, this much current, with a latching current of 250 milliampere, holding current of 150 milliampere. IG max 150 milliampere, IG min 1 milliampere. The SCR is connected to an inductive load where L is this much millihenry in series with a small resistance of 1 ohm, and the supply voltage is 200 volt DC. This one. The forward drops of all transistor diodes and gate cathode junction during on state are 1 volt. What should be the approximate minimum value of R? So they are asking minimum value of R. R means this resistance. Minimum value of R means maximum gate current will flow. Now you see they are saying that all the forward drops are 1 volt. So if we have 10 volt here, then 1 volt drop comes here when Q is on. So what we have is 9 volt. Now it's a 1:1 transformer, so 9 volt. So if I talk in terms of this ground, then this is at 9 volt, and another 1 volt drop here in diode D1, so this is at 8 volt. On the other hand, gate cathode junction diode during on stage is also 1 volt, so this voltage is 1 volt, so this is at 1 volt. So basically the voltage that we have across the resistance VR is 7 volt. Now, so they are saying minimum value of R. Minimum value of R means that should be allowing the maximum gate current, which is 150 milliampere. So R main should be 7 by 150 to the power minus 3. And how much is it? Should be somewhere around 47. Yeah,
46.6.
46. I take 47. So it should be 47 ohm. This is easy. Okay. The next question is the minimum approximate volt second rating of pulse transformer suitable for triggering the SCR. You see, volt second means, what is volt second? Volt second is flux linkage. Okay. Anyway, so basically we have to, they are saying that suitable for triggering the SCR should be. Now try to understand what they want to know here. We already know that a 9 volt drop comes in the transformer primary. The volt is already known to us. We have to find out the second, that is how long we should turn, or how long we should keep Q on, keep the switch on. Now if you see, here we have as a load we have RL circuit, right? Now RL circuit current increases like this, looks like a BH curve, not like that, something like that. It increases like this. So we have to find out how long does it take to, how long does this current take to reach the, which one, latching current or holding current?
Latching current.
How long it will take to reach the latching current. So that much time is the minimum time that we must keep the um, switch Q on. Now this is easy. You already know equations. So what does the current look like? It is V by R 1 minus e to the power minus t by tau, right? Our latching current is 250 milliamps, so it comes out 250 10 to the power minus 3. Voltage is 200 volt, resistance is 1, t by tau. So from here let us first find out t by tau. Can you tell me quickly? T by tau should be this, minus ln just evaluate this on your calculator. Do it and tell me the value of T by tau. It is no longer T actually. Let us call it TL, because we are already giving a value to current, so we cannot keep it time variable anymore. So TL. Are you doing? How
Yes, sir.
long does it take?
No, we are not having access to calculator. So it is
Wait, ln1 minus this is 1.25 10 to the power minus 3. Now, so what is the time that we must keep it turned on so that the thyristor is turned on permanently? This should be to tau. Tau is L by R. L is 150 millihenry. L is 1. So this times 150 10 to the power minus 3.
is 0.00125 T by tau.
Hmm. So this much time we have to keep. So if I write it in microsecond, it will be this much microsecond. There is a minimum time we have to keep the switch on. We have to keep the or we have to give a gate pulse Q. Now we have the time, so volt second we can find out, that will be simply 9 times TL. 9 is the voltage that is coming. Some 1688 microvolt second, or 89 maybe. So this is the required volt second for the transformer.
So the switch need to be kept on for this time of 187.6 microseconds.
Yes. If you withdraw the gate pulse before this time, what will happen is your thyristor will be damaged. Can you tell me why?
Because this anode cathode current will keep. Don't know, sir.
If I withdraw the gate pulse before the current reaches latching current, see the latching current is around how much, 150 milliampere. So the latching current reached somewhere near 100 milliampere where I withdraw the gate pulse.
Oh,
So the thyristor will immediately stop conducting.
okay.
It will turn off.
Oh,
But this is an inductor.
okay.
It
Oh.
cannot handle a thyristor turning on that first.
Mm.
So that will damage the thyristor, the stored energy.
Okay.
All
Even though it
right.
is a minimum current,
Mm-hmm.
even though before turning on, minimum current will be some less current will be flowing through thyristor. Even that from that change itself is sufficient to damage the.
See, we were now whether that ultimately that is the heat energy flowing. Okay, there is a heat energy that is dissipated across the switch. Okay, now ideally speaking, even a microampere of current, means I'm saying theoretically speaking, even a microampere of current can create infinite voltage if you interrupt,
Okay.
because it is V equals L di dt.
Yeah.
Now infinite voltage can never come because there are large impedances in the circuit.
Yeah. Because the
I shouldn't say,
ability
means
can.
DRT cannot be dropping that sharply. First of all,
Mm.
secondly, whatever stored energy the thyristor have, that sorry, the inductor had, that thyristor might have the capability to discharge to dissipate that much, because it is a 1.5 kV 250 ampere thyristor. It might be having huge heat sinks also, so there's a good chance that
Mm.
it can dissipate. But mm, theoretically, if we say, that can
Mm.
create infinite voltage across the thyristor,
Okay.
or very large voltage across the thyristor, and if it cannot uh, withstand that much, it will fail.
Okay.
Okay, one more question. This is regarding snubber. Before going into snubber, let me go into this question. Let me discuss a bit about snubbers. Not much, it's already there. So snubbers are also sometimes called SANs, which is switching aid networks. Okay. Mm. So what you must keep in mind about snubber is that snubber does not reduce switching loss, or in other words, does not increase efficiency. Okay. What it does is it shifts the loss from the switch to the snubber resistance. So if you look from the switch point of view, it will look like uh, yes, the switching loss is avoided. um, Maybe the voltage spikes that I was talking about some classes back, that if you have leakage inductance, then when you turn off a switch, you actually get a voltage like this. So these peaks snubber can reduce and all. So overall the switching loss will be, sorry, overall the heat dissipated in the switch will be reduced, but that heat is getting dissipated somewhere else, that is in the snubber resistance. Okay, so the snubber protects the switch, but it does not reduce the loss or increase the efficiency of the circuit. All right.
Sir, it makes sure that this snubber makes sure that the dv by dt is within the rating of datasheet rating of the device.
Yes.
Okay. So, but sir, actually, uh, okay. So the device manufacturer itself. So this spike, it will be varying based on the application we are using.
This spikes depends on the leakage inductance that you have in the circuit, the stray inductance that you have in the circuit.
Okay.
We discussed this in flyback, I think,
Yeah, yeah. We
that
discussed this one.
that the stored energy that goes to the other wind, means it was in the transformer core, and it starts flowing in the other winding. But if you have a leakage inductance, that energy, that is not mutually coupled, that is why it is leakage. So the energy stored in this leakage, this is not going to the other, to the secondary, but you are
Yeah.
interrupting the current flowing through it. So this
Yeah.
energy must be dissipated somewhere. That is where you need this.
Reset.
Just a minute. Yes, RCD. Sorry, it will come across the switch. Okay.
Sir, for including basically in our forward converter for flux reset, we are not including this leakage inductance.
It's not that we're not including this leakage inductance. The reset circuitry in forward converter that makes sure that the stored magnetic the stored energy in the core, that is either dissipated or um, it is given back to the source. Now if you look at this uh, topology, let me draw the equivalent circuit. So if you look at this topology, you see this winding and this winding, they are magnetically coupled, right? Now
Uh,
when you turn off this switch, the energy stored in the core, that only will travel, or that only will uh, travel back to the supply from this core, but the energy here, that will not.
uh,
But if you think if you consider a lossy reset circuit like this, if you think, then yes, the whole energy stored in both leakage and magnetics, sorry, just a minute, something is wrong, yeah, that is dissipated in this resistance. But in this case, where you have this reset circuit, you are resetting through magnetic coupling, the energy stored in the leakage, that will be dissipated across the switch. But here it looks like the whole energy in both this inductance and this inductance, that will be lost in this resistance. Looks like that in this case the switch will be less relief, sorry, more relieved of such stresses.
okay. In the lecture, there is also some other circuit for considering this leakage inductance. They have used some two switches, and the diodes are used to dissipate the energy from the leakage inductance into the source. Yeah, what you said we understood, sir. This one is right. We
No, you
understood.
cannot dissipate leakage inductance energy separately,
Okay.
because you see, if I draw the, sorry, if I draw the equivalent circuit, then the two terminals that are available to you are only this and this. you cannot avail this terminal
Okay.
because this leakage inductance is a lumped parameter. Are you sure that it was written they give back the leakage stored leakage energy to the supply?
Yes, sir. Sir, I will share that link, that
Okay,
video
okay, then
link.
I maybe there's something I don't know. Okay, maybe there is something I don't know. All right, we will start with our last problem for today. It is a snubber circuit. Mm, what kind of snubber is this? Is this a turn on snubber or a turn off snubber? This is a turn on snubber. So the thing is that if there is some capacitor present somewhere in the circuit during turn on, that may discharge, or the stray capacitance or the whole capacitance of the circuit, that may discharge the stored energy through the switch when you are turning on the switch. So suddenly the switch, when it is turned on, may see a large spike in current. Okay, so to prevent that, we have an inductor. Why? Because inductor will prevent any kind of sudden change in current. So this is how it works as a turn on snubber. All right, so
Sir, I have shared the link.
yeah, I've seen. I'll look into it. Okay, so the question is, assuming linear fall of voltage across transistor at turn on, falling from V to 0 at time t2. So if I call this as VCE, say, so when it was off, the voltage was full voltage V, and then it drops like this to 0. So this time interval is t2, and this is the waveform for VCE. Okay, and the current, okay, expression for snubber inductance L, which will delay the rise of current to its on state value in a time of t1. So the current was 0, and not necessarily they happen together. Let me not draw them together. Something like this. The current I. See. Okay. Now the thing is, this whole phenomena is a switching phenomena. Okay. Now, if you look at the load first, so when the switch was on, this was carrying some constant current. Okay. And when the switch is turned off, what happens is the inductor, it dissipates its energy through this diode in this resistance. Okay, through this diode the current flows and it dissipates its energy in this resistance. So we can say that when this switch is again turned on, either the load is completely dissipated, means there is no stored energy in the load, or meaning the load inductance, or the diode or maybe there is still some energy, so the diode is still on. So what I mean to say is, if I write KVL, V equals, say, I don't this voltage, if I write VL plus switch voltage VCE plus V load, this thing can essentially be taken as 0. Why? As I said, there are two possibilities. One possibility is that the diode is still conducting, okay, so that is 0 in any case. Secondly, second possibility, even if say the diode is not conducting, the energy is already dissipated completely, but still we can say that since this is a switching phenomena and this is an inductive load, it takes some time for the load to start conducting, so we can essentially keep it 0 for this small duration load voltage. Okay, so from here what we can write is, what do we have? We have the equation for VCE, right? VCE is capital is y equals mx plus c. So if I take the origin here, then m is capital V by T2 times T plus C is V. So if I take V common, 1 minus T by T2. Okay, so it is VL plus V times 1 minus T by T2. So this V gets cancelled out. Now if I keep it here, then it becomes V T times T2 equals VL. VL is again L di collector dt, the same current is flowing through them, right? So what we have is, say, V by T2 times T dt is L dic. If I integrate them, where do I need to integrate? See, this is a variation of IC, so we have to integrate from here to here. This whole duration is T1. Let's take the origin here for the integration. So if I say T varies from 0 to T1, then IC varies from 0 to full value I, right? Then what do we have? We have V by T2 times, this becomes T1 squared by 2 after putting the values. T squared by 2 equals 0, yes, then this is only Li. So from here we can say that the required snubber inductance will be V times T1 squared by 12 T2. So this is the inductance that we will need for this operation.
2I T2.
2I, oh yes.
This I is that on-state current.
Steady state on state current.
Okay. Sir, but actually during turn on, when the current reaches to the maximum value, then only the voltage will start to drop.
Yes, but I do not think that will change anything here. No, okay, wait, let me make a statement like that. No, but do you think in the whole calculation, you see, we anyway took it at some abrupt point. That is not changing any calculation, right?
Yeah, we have taken T1. So,
And also this starting point we have taken at some abrupt point. This I have not defined.
okay, yeah. So this inductance is now This rubber is now through this L. Uh, it is uh, it is limiting this di by dt.
Di by dt, yes.
So now it takes more time to reach the steady state on state value.
Yes. Otherwise, the stray capacitances, they tend to push a large spiky current through the switch when it is turned on.
Oh, stray capacity across collector emitter.
No, not only there, other capacitances in the circuits, the track capacitances, everything. Not only stray, other capacitances also in the circuit.
Okay, sir.
Okay, anything else you have to ask?
Oh, sir.
I discussed these circuits, these kind of networks. Say if you have, okay, for the sake of simplicity, I'm drawing IGBT. So if you have a resistance like this, R1, the gate resistance, it is possible to have different turn on and turn off times, or maybe faster turn off or faster turn on than turn off. So what we do is, if you want to have faster turn off, you just connect a diode in this path and a parallel resistance here R2. So basically when you are turning it on, the effective gate resistance becomes R1 parallel R2, while turning it off, effective gate resistance becomes, sorry, this R2 becomes only R2. So your turn off resistance is larger than turn on, so your switch turns off, so turns on faster than it turns on off.
Sir, this R2 is lesser, right?
Doesn't matter, if one resistance comes in parallel, that is anyway going to reduce the overall value, no?
Yeah. But at that time, for faster turn off, we want this R2 to be lesser than R1.
No, in this case turn on is faster. We have small resistance while turning on.
Ah, yes.
Or else you can have what to say, this is unusual, but you can do this if you want different turn on and turn off times for some reason.
Yeah, now only single path is there, no parallel path.
Yes. So turning on goes like this, turning off goes like this.
So usually in these switches, the turn off times are higher now, sir. So that has to be
Yes.
reduced.
Yes.
So here R2 should be lesser in this diagram.
So you can have in that case surface like this. I do not want to change it here once again. So if you have like this, then your turn on resistance is only R1 and turn off resistance is R1 parallel to R2. So your turn off is faster.
Okay.
Many times we realize faster turn off by using totem poles in this fashion, that You have two sources, say they are realized in several ways. There, say one 15 volt and one 5 volt. It's a common ground, and you have a totem pole like this. Sorry. Okay, your gate signal is coming here with respect to this ground, and your switch is here. Say I'm drawing a BJT like this. So when you are turning on, means you are, sorry, you are turning on Q1. So what happens is the current flows. You see, turning on means you're giving a high pulse. Giving a high pulse means Q1 is on, Q2 is off. So
Yeah.
the current flows like this. It goes to the ground like this. So the turn on voltage is 15 volt. Now, say if you have, say in the previous circuit, if you look, if you have things like this, your turn off voltage is 0. But in this case,
Mm.
in this totem pole, there is a possibility of having a turn off voltage of negative,
Yeah.
because when you are turning it off, when you're keeping it low, the current is flowing like this. Mm, how
Through
is it
Q2.
flowing? Just a minute. Yeah, through Q2 is flowing like this. So the turn off voltage is minus 5 volt now. So the charges are drained out even faster. But if you do not have a fast turn off requirement, you need not to make this circuit.
Sir,
Yeah.
sir, here in this the totem poles Q1 and T2 are connected
Hmm.
by the same bases are connected.
Hmm.
Sir, for suppose Q1 is to be made on at
Hmm.
that time, uh, compared to the center point of Q1 and Q2, uh, the the connected terminals should be greater than zero point 0.7 at least. The
So
Q1
what
and
is
Q2
it?
are connected,
Hmm.
sir. Suppose if I want Q1 to be on,
Hmm.
then there is a midpoint between Q1 and Q2. Between emitter of Q1 and emitter of Q2, there is a
Yes.
midpoint.
Hmm.
So from that point to the terminal where two bases are connected. So with that point, with respect to
Hmm.
this center point, should be greater than zero point 0.7 for Q1 to conduct.
Okay.
How that is realized? Similarly, if I want Q2 to be on, this has to be lesser than by zero point 0.7. So how that
Okay.
potential
One
comes
thing
here?
I think I missed here. There's a resistance. Anyway, just a minute. Which two points you were saying? I'm not very clear.
Sir, between the emitter of Q1 and emitter of Q2, there is a midpoint.
Just a minute. I will draw it once again. Yes, this point. No.
Yes, at that point. Yeah.
Hmm.
With respect to that point, the bases of two Q1 and Q2 are connected. So that point should
Hmm.
be greater than zero point 0.7 for Q1 to conduct.
Hmm. No,
Sir, how that?
the base signal is coming. No, your the command signal when to turn on the switch, when to turn off the switch, that is coming from here.
Yeah, some 15 volts or
Whatever
some more.
voltage that you
Uh,
have in the inner control, and you design this R value, say R1 I write. You design this R value such that you have enough base current to turn on Q1 or Q2. And the base current of Q1 also completes its path through this switch.
Oh. Mhm. So the for faster turning on of Q1, this R1 should be less.
Shouldn't say less, you have to design some value. Generally, it is a small value, 22, 47 or 2.
So similarly, when Q2 is on, it flows through the opposite.
Hmm.
Same
Hmm.
through R1 and ground, and then through IGBT.
Yes.
So all the energies in the capacitors are dissipated in the resistors during turn off.
During turn off, yes. No, if in this case, if you have this minus 5 volt, means the objective of this 5 volt is to get back that energy, the stored energy, faster. So they are going back to this.
Oh, yeah, the ground is connected there also.
Hmm.
So we need some capacitor across that 5 volts, sir,
Just a minute. No, no, we do not need a capacitor as a 5 volt. How is
across
the
the 5
current
volts.
flowing? Just a minute. How is the current flowing? Let me remove. If I have one like this, so when I'm turning it off, it goes like this. No, I think yes, the capacitor stored energy, this stored energy, it is dissipated in this resistance, and then it is charged with a 5 volt polarity but in reverse direction. If you make an arrangement like this,
Uh-huh.
because you see the whole time the this battery is supplying.
So CGS has to come from, for turning off, CGS has to come from plus 15 to minus 5.
Hmm. If you want a fast turn off,
Uh,
Excuse me, sir.
yeah.
During turn up,
Hmm.
how much will be the voltage across this discharging tungsten?
It's 5 volt or minus 5 volt in this case.
5. Can we assume the voltage is equal in equally divided between Q1 and Q2?
Q1 and Q2 are never on together or off together.
Yeah, yeah. These are totem pole.
Yes, so when Q1 is on,
Hmm.
then Q2 is how much? It is now blocking 20 volt and
Okay,
vice versa.
okay, okay. Minus Q1 drop, right?
Minus Q1 drop, yes.
Okay.
so similarly, during turn on, the midpoints of the voltage sources and the emitter of IGBT are connected during turn on.
Midpoint of
During
voltage
turn on,
source and emitter of IGBT is always connected.
no, no, the current will flow through that path
Yes, for
during
turn
turn
off
on.
also it will flow to that part, isn't it? You have to connect them to the same ground.
Ah, yeah. So,
This
but the
whole
current will
thing
flow
is
through 15.
the gate driver part. So your gate driver ground, gate driver power supply ground, your this signal ground. this is already been isolated from the control. I think you understand it now. This has
Oh,
already been isolated from the control. So
okay.
all these grounds, they must be the same, and the source or emitter of the switch.
Okay. Okay, sir.
Yeah. Do you have anything else?
No, sir.
If someone has some more question, I will try to answer, or else we will conclude for today. We don't have much content for today. Mr. Devkar, you have something to ask?
Hello.
Hello.
I was late today.
Yeah, we were discussing gate drivers, but today's content was not that much. Mostly known things. Mostly we discussed about why isolation is required and two types of isolations: optical and galvanic isolations, and how MOSFETs are turned on, Miller plateau voltage, and other things, and two problems will solved.
I have to see the video then.
Yes, I will upload it today only.
Okay.
Sir,
Yeah.
how can you ensure that during off time this capacitor,
Hmm.
discharging capacitor,
Hmm.
this gets discharged completely?
Uh, Even if we do not consider this circuit, say if I have okay, let me draw a general gate driver circuit. Okay, so this is the one. So if I have the, since we are talking about capacitors, let me draw MOSFET. So our objective of gate driver is to charge or discharge this capacitor. Right.
Right, sir.
Now, say if I write this as small Vg, and this voltage is our VGS. Now when I want to turn on the switch, what I will do is I will give a high VG, say some 15 volt or something. Okay. Now what will happen is, if I look at this circuit, this is nothing but RC circuit,
Yeah.
right? So if I write this VG, VGS, so this will charge like this, even faster, much faster. Say like this, it will charge. Okay. Now after this, at this point I want to turn off the switch, so I make VG as VG0. Okay, now 0 means what? This is virtually short circuited. So now the circuit looks like this. Now the circuit looks like this. Now the capacitor has no other option other than discharging completely. Or if you give a negative VG, maybe generally of smaller voltage, then also the circuit looks like something like this. So it will discharge, then charge to other negative values. So it will maybe look like this.
But sir, discharge rate will depend upon resistance.
Yes, that is the thing. So you have to make sure, depending on your switching frequency. So if I write, say, your switching frequency reciprocal, which is the time period, that should be more than, at least, this equation is clear.
Yeah.
So basically, we are talking about the criteria to design RG. What will help us
Yes, sir.
decide the values of RG? One thing is um, is how fast you want to switch, and that would also be a constraint. On one more constraint will come from the switch side, how fast it can switch. And secondly is you have to turn it off also, so that um, it is discharged completely turned off. Generally I have written 5 here, but it is kept much more, much more, because your turn off time should not be, means the time that it takes to turn off, that should be maybe 1/10 of the whole turn off period, or maybe even less.
Ah. Sir,
Yeah.
sir, here this instead of this 1 by Fs, the T off should come, right?
T off, yes, T off. So I should write on the list. Now if you see that you cannot fulfill these two criteria with one resistance, what you can do is you can have this kind of circuit.
In this circuit, during off time, this RC and this resistance will be in parallel, so it will be faster.
Yes.
But during the on time,
It will not be that fast.
yeah. Okay, sir.
Yeah, more questions? Next we will discuss closed loop control. We will see how much we will have to discuss. So basically what happens is this closed loop controller, whatever we have, say the closed loop controller that delivers D. How does it deliver D? It delivers D in terms of some V, control voltage Vc. Now we compare that with a sawtooth and generate a pulse, say not like this, and generate a pulse like this. This pulse is then fed to a buffer maybe. So the pulse comes, the pulse is fed to a buffer, because the pulse is maybe coming from a microcontroller that cannot give that much current, so buffer like CD4049 hex buffers and other buffers, or you can simply use an op-amp in this current, in this voltage follower mode. Like this. Yeah. So this can now supply the current. It does not draw the current from the microcontroller. Now this buffer, then it feeds to the optocoupler. Then the optocoupler directly feeds to the driver IC. That can be a driver IC, or you can have a total or whatever. And there is an isolated power supply that gives power to this driver. Actually, I should have written in blue from here itself. This then drives the switch.
Sir, what is this buffer you're talking about? Is this some kind of isolation or?
No, not isolation. Buffer is some, see, this pulse that is coming from some microcontroller. Okay. And the microcontroller may not be able, because optocoupler, you see here, this is an optocoupler. Say this one, see this green box. Okay. in optocoupler. So basically, what you have to do is you have to turn on a diode inside. Okay,
Ah,
you have to turn on a diode inside so that the diode can emit infrared and turn on the transistor on the other side. Now, your controller, the microcontroller, that might not be able to give that much current. Okay, and even if you
okay.
try to draw that much current, what will happen most of the cases nowadays, the advanced microcontrollers like say TMS320 and all, they have current limiting. They will either trip the output voltage, or your output voltage for other controllers, it may say this thing gives you 3.3 volt as high, but you are trying to draw current also from this high source, this voltage will
Mhm.
drop. Okay, you will not be able to turn on the diode at all. So basically
Okay.
what I'm trying to say is controllers have large voltage regulation and they do not have that much of current sourcing capability. For that,
Okay.
you need someone which will source the current.
Mhm.
So if you have an op amp like this, if you have an op amp like this, so whatever voltage is here, that much voltage is here. But the thing is, the op amp has a power source, say 5 volt or 15 volt. The current that is coming outside the op amp is actually coming from this power source, not from here.
Okay. Oh.
So the load current, so the microcontroller is not loaded.
Ah,
So this CD4049 that comes, that is a hex buffer. So it is an IC. So hex buffer means you can understand there are, so it is like this.
six.
Yes,
Six.
yes. So something like this it will have inside, and there is some, actually it is bidirectional as far as I can recall. So there is some direction select pin. If you keep it, if you tie it to high, direction will be something, and if you tie it to low, the direction will be the opposite. So it is possible to control the direction also for those buffers.
Oh.
Sir, how much is the current drawn from the one single buffer in this case?
I have forgotten, but CD4049 has no, I don't remember.
Maybe in some few milliamperes
Yes, milliamperes definitely, but how much I don't
to
remember.
10, 20 milliamperes. Or
Maybe
something.
something like that.
So
Well,
it
with
has
this,
to be in parallel, then it will be a multiple of that 6 into 20, somewhere 120 milliampere or like.
That much is not required.
Then how much?
One buffer is enough, means they are made like that, that one buffer is enough to drive an optocoupler.
Okay.
These hex are not to make them parallel. You understand why this hex thing came? Why at all hex? Because in inverter you have 6 switches. So for one inverter you will need one buffer AC. That's all.
Sir,
Yeah.
this buffer purpose is to give the higher current sourcing capability without decreasing the voltage.
Yes, without loading the controller.
No.
so in your a closed loop,
Hmm.
some PWM technique you have utilized. There, what will be the switching frequency? It is a sawtooth or
Yes. So whatever switching frequency you need in your power circuit, the sawtooth should also have the same frequency.
okay. So switching frequency means sawtooth frequency.
Yes.
So this will give you variable with pulses. It means D and 1 minus D will be variable.
Hmm. So if you look at this voltage, this VC, what I said here, that is being compared with the sawtooth, this duty ratio is directly proportional to VC. You can prove it also by using simple similar triangle theorems. Just apply similar triangle theorem in these two triangles, this large triangle and this, I'm showing it here, this small triangle. All right, then if not anything else, we'll stop for today. And next we will talk about control circuits. I will upload this video right now. Maybe after 5-6 hours it will be available on YouTube. It takes some time to process the video by YouTube. Then you will get to see if you have missed from the beginning.
Sir, in this, to control the duty ratio, this VC is used. Similarly, if we want to increase the switching pulses frequency, then the sawtooth frequency needs to be increased.
Yes, I think I discussed about this. Just let me see. I discussed about one IC. This SG352 for this IC.
Yes, sir.
It does this thing actually inside. So here I have forgotten the pin number, so do not exactly take my words. But it's a DIP package. So DIP package, what happens is numbering starts from here. If this is 1, this is 8. At 6 and 7, at 1 you have to connect resistance, the other you have to connect capacitance, and the frequency is a function of this resistance and capacitance.
Okay.
Variable capacitance is not that much available, or maybe it's expensive, so what we do is we keep a capacitance and keep a pot here in place of the resistance. We vary it and fix the frequency. Most probably at pin number 3 you will get to see the, if you put the oscilloscope there, you will get to see the oscilloscope. And most probably at pin number 2 you have to give the VC. And most probably from somewhere pin number 10 and 11 you will get these two pulses. Just a minute, it's not working. Yes, this S1 and S2, these two pulses you will get.
Okay.
I have forgotten the pin numbers. Somewhere here will be your grounds or power supply will be somewhere here 5 volt. Probably a pin number 8 was ground.
For varying this VC also, some parts can be used, sir.
This VC comes from your control circuit, or maybe you can manually vary it using a pot. This VC comes from your control circuit.
By sensing the output voltage.
Sensing output voltage and then implying whatever control algorithm you want to do. Not implying, implementing whatever control strategy you want to do.
Sir,
Yeah.
there are current mode controllers also, no? Double-ended.
Yes, there are. I think I don't know what will be covered. I will see what we'll
3825
discuss.
or like that, and 3846 like.
I think yes. I mean the common control strategies and all they are embedded in those ICs, so that you don't have to make your own circuits.
Yes.
These are sometimes called, ASIC. Application specific integrated circuits. So maybe at your research
मॅडम
level.
कडे गेले ते
Uh-huh.
नाही.
So maybe in your research level, you develop a circuit with transistors, resistance, capacitance, and all, a large circuit. Now, once the circuit is finalized, you want to make a huge number of products. Same circuit board, you want to make huge number of products in an industry scale. So what you do is, instead of having such a large circuitry, there might be mistakes. You make one ASIC, produce it in bulk, and put it in your circuit. What happens is, you make it small, it makes the whole thing small. The possibility of error reduces because you have many devices here, rather you have one IC here, one monolithic IC. So it overall becomes compact. So things like that are being done, like there are buck converter IC directly. Okay, so you do not need to make a controller separately and all. You have one dedicated IC for controlling a buck converter, like that.
Topology specific, isn't it?
Yes, yes. Dedicated ICs are there. Like one IC I not discussed, just mentioned once today, this MC33153. This is one IGBT driver. So you do not have to worry about anything. Simply give it the power supply it requires, connect the switch outside and give it the pulse. It will do everything inside. All kind of DSAT protection, required power supply, sourcing current capability, sinking current capability, everything it has inside. You not worry about anything. Okay, then we'll stop for today. We'll meet next day with controllers.
Okay.
Good night, sir.
Closed loop controllers. Yeah.
Okay.
Thank you, sir. Good night.
Yeah.
Thank you,
right.
sir.